if you have two finite sets, A and B, where A is your domain and B is your codomain, how many onto functions can you create between the two sets? Well, in order to answer this counting problem, we need to understand what an onto function is. Now, to remind ourselves, a function is onto if for all elements in your codomain, in this case B, there exists an element in our domain A such that the image under A is equal to B, or the image X under F is equal to B. So what does this mean visually? Well, it means the following. If you have your set A and you have your set B, and we have some elements, let's say in our A and some elements in our B, for a function to be onto, it must be that everything in B can be achieved from an arrow pointing from A, or a function. So for example, if we had a function like so, this function would in fact be onto because for every element in our B, there exists an element A that you can plug into your function to get the B. So this means that if we had a function that looked like this instead, for example, like so, and we just had an element like this, this would not be onto because it's not all elements in B. There is one element in B where there does not exist an element A, where if you apply the function to an element in A, you're going to get this element B. It's just not possible. So what this basically means is an onto function is a function where you can get everything. You can map everything from A onto something in B. There is nothing in B that is lonely like this element. In order to solve this problem, we're going to need some more definitions, and let's use what we should already know, and that being how many total functions can you create between two finite sets? How do we know that? Well, first let's define two things. First thing we need to define is the size of our domain A. We'll label that as the variable A. The size of our codomain B is going to be, we'll label this B. So what does this mean? The size of A is simply saying how many elements are in A. If there are 4 elements in A, then the size is equal to 4. So in this case, A would be equal to 4. Similarly, if A only had 1 element, the size of A would be 1, and so this would be equal to 1. Similarly for B, if B had 3 elements, then this would be 3. If it had 4, it would be 4, so on and so forth. Okay, so it's good that we've clearly defined some notation for our sizes. Next, what do we know about counting functions? Well, we know the total number of functions you can possibly create from A to B, when A and B are both finite sets, is going to be B to the power of A. We're looking at the lowercase letters here. So it's going to be the size of B to the power of the size of our domain A. So we know what the total number of functions possible are, and we know intuitively there's probably going to be quite a few of them that are not going to be onto. So what am I thinking? Well, this is what I'm visually thinking when I'm going to try and solve this problem. So what did I draw here? Well, picture this huge bubble to be the set of all functions f you can make. So the number of things in this bubble is going to equal to b to the power of a. Now what do we know? Well, the possible functions you can have are going to be functions that are, in this case we'll label the dot to be functions that are not onto and not one-to-one. We'll label the star to be functions that are, actually no, we'll leave the star for later. Let's say the square is going to be functions that are one-to-one but not onto. We'll say the star is going to be functions that are onto but not, oh, I'm using the symbols for one-to-one, not the words, one-to-one. And finally, we'll say the line is going to be bijective, which simply means they're both one-to-one and onto. Those are the 4 different categories of functions we can have. Functions that are not one-to-one and not onto, functions that are one-to-one but not onto, functions that are onto but not one-to-one, and functions that are bijective, which again means they're both one-to-one and onto, so the opposite of this first one here. Now, what do we want to do? Well, we know the total here when you add all these types up is going to equal to b to the power of a. So what can we think of? Well, what I'm thinking we can do is it might be easier, instead of counting these two categories, because these two categories here, the star and the line, fit exactly what we want to be able to count, it might be easier to instead count this type and subtract them from our total. So what is that going to look like? So because I know we want functions that are onto, we do not want to count these two categories because they are not onto. So what does that mean? We take our entire total and we're going to take away these two types of functions that we don't want to include in our counting. So what is that going to look like? Well, it's going to look like this. So I've taken away the functions we don't want to count. We don't want to count functions that are not onto, right? But we do want to count these two functions here. So when we take away the ones I've circled in red, we are only left in this bubble with the functions we do want to end up counting. So what does this mean? This means that the logic I'm thinking might be easier to compute and derive is going to be to say, take the total and subtract these two red categories of functions. And what am I going to call them? Well, we can just call them subtracting what we don't want, right? So we could say this is the same as saying our strategy to be able to figure out how to do this is going to be to take the total and subtract what we don't want, right? As you can see here, it makes intuitive sense. We have the total, take away what we didn't want, these two categories, and all we're left with are what we want to count. So let's go ahead and turn this into math. Okay, so I've rearranged some of the information we're going to want to keep in mind over here, so we have some more space for our working out. So again, to reiterate, what did we figure out? Well, we figured out our strategy and logic to be able to count this is simply going to be to take the total number of functions and subtract what we don't want to count, because then we'll be left with what we do want to count. Now, the goal now is to put this into math, this logic here, this goal into math. Well, what do we know? We know the total is already going to be b to the power of a, so we just have to figure out how to put the part underlined in red into math as well, since we've already gotten half of this into a mathematical formula. So how are we going to do the second half and get a mathematical expression for it? Well, let's maybe start by doing some examples and see if we notice any sort of patterns. Let's take the following example. Okay, so I've created just some arbitrary example of A and B. In this case, the set A contains these 4 elements and the codomain B contains these 3 elements. So what do we immediately know? If we want to create a function that goes from A to B, the total number of possible functions we can have is going to be 3 to the power of 4. How do I know this? 3 is going to be the size of our domain, or codomain. The size of our codomain is going to be the number of elements in B. There's 1, 2, 3, so that's where we got the 3 from. How do I know it's to the power of 4? Well, that's going to be the size of our domain, our A. So how many elements are in A? We have 1, 2, 3, 4. That's where I got the 4. So we know that the total number of functions you can create here are going to be 3 to the power of 4. Now, let's focus on the part I've underlined in red. What can we think of? Well, first, let's think of the easiest possible case where the function is not going to be onto. So what do we need to do? We simply need to think of, well, how can we create the easiest function where not everything in B can be gotten from an input of A into the function? So what can we think of? Well, the easiest example you could think of a function that is not onto is going to be, well, what if there's at least one element in B that we can't map to? So what does that mean? That means, let's for example say our function does not map to the element 1. So what is this going to look like? Well, for example, it could be a function that looks like this, where we have A and B mapped to 2, C and D mapped to 3. Right? This is a function, but it's not onto because the element A does not have any arrows going to it. So let's think about that more logically. Regardless if we drew arrows in any way here, how could we mathematically describe this kind of relationship? Well, Here's the way I like to say, this is the way I like to describe it. This is not concrete or really correct, but it works. So when we're taking our set A, in this case containing the elements A, B, C, and D, and we have a set B containing the elements 1, 2, and 3, what we notice is we're mapping these like this, right? For this example, or any orientation of these arrows. But the important point is, because we are mapping nothing to 1 in this case ever, nothing's ever going to map to 1, you might as well pretend like the 1 isn't there. You might as well pretend like your B only consists of these 2 elements because the 1 doesn't do anything. No one's getting to the 1. So we just pretend like the 1 isn't there in that case. And what do we find? Well, how many functions can you make where you don't have a 1? Well, it's going to be something that looks like this. You just pretend your B, your codomain, shrank in size, and now it only contains the elements you are mapping to. So how many possible functions can you create here? Well, it's going to be 2 to the power of 4. How do I know it's going to be 2 to the power of 4? Well, because we're ignoring the 1 that used to be here, right? We're just getting rid of it. Well, we're just pretending like B just has 1 less element, which just means the size of B is going to now become 2 because there's only 2 elements left. The size of A didn't change. So the total number of functions where you don't map to 1 is going to be 2 to the power of 4. Okay, that's a great start. What else could we think of? Well, what if instead of not mapping to 1, we think of, well, let's take another element, right? We can choose to not map to a different element. What if instead we chose not to map to the element 2? Well, what would that look like? Like this, right? You have no arrows going to your 2. So what does this mean? This means if you were to take your set A once more, and your set B once again, because nothing is mapping to 2 in this case, just pretend like it's not there. The 2 might as well not have been in your set B. So what do you find then? Well, then you find that, of course, your function will be like this. Nothing ever went to 2. We ignore the 2 is there. How many functions can you make? How many different ways can you arrange these arrows so they only go to 1 or 3? Well, the answer is going to be 2 to the power of 4, which is unsurprisingly the same as our case with functions that don't include 1. So this is also going to be 2 to the power of 4. And for the exact same reason, you're going to find that when we want to exclude one element, if we chose 3, it would be the same here. There are 2 to the power of 4 functions that do not include a 3, or do not map to 3. Fantastic. So what do we find here? Well, we found that if we want to exclude one element so that it's not on 2, we find that it looks like this, right? The equation goes from 3 to the power of 4 to 2 to the power of 2. Okay, let's keep that in mind. Let's, just for the sake of example, try a slightly different example very quickly. Okay, so in this case I've made a smaller example, and let's similarly name these elements A, B, C, and then 1 and 2. So let's say we want to ask the same problem. What if I don't want to map to at least one element? I want to see how many functions are not going to map to 1. Well, we're going to be left with functions that will look like this, right? These are all the functions that won't map to 1. And what is that going to look like? Well, you write out your A, B, and C, and you write out your B, which is going to be 1 and 2. And because we're not mapping anything to 1 to make the function not onto, you just pretend like the 1 isn't there. So how many possible functions can you create that don't map to 1? Well, it's going to be 1 to the power of 3, right? Because you only have one element left in your set B, your codomain, and you still have 3 elements left in your domain. And you're going to find the relationship is going to be, or the number of functions are going to be the same for both cases here. It's going to be 1 to the power of 3 and 1 to the power of 3, regardless which you choose not to do. Okay, and of course we should note here that the total number of functions you could have made without this rule would have been 2 to the power of 3, because it would have been the total size of B to the power of the total size of A. Okay, now we have a little bit more information to maybe figure out a pattern that we notice. So now we have 2 examples, and I'll let you know now that this is more than enough to make the following argument. Notice that when we want to get rid of one element, right? We want to just not map to one element in our codomain. What we notice is it seems like the base here, the bigger number at the bottom, seems to go down by 1 in both cases. We went from 3 to 2 and from 2 to 1. But our power up here didn't change in either scenario. So what could we think about this? Well, this means that it looks like the pattern here appears to be the size of b minus 1 to the power of a, right? This is the relationship we've just found for the number of functions that are not onto because one element is not being mapped onto for sure. So that's the relationship we found so far. Let's go ahead and maybe push this a little bit further. So in this case, instead of saying let's not map to one element, let's instead say, what if we don't map to two elements, right? So let's, for example, say we're not going to map anything to 1 or 2. There's going to be no arrows going to those two elements. So this means the function would look something like this. There we go. And what can we see? Well, you take your set A and your set B, and we're mapping everything to 3. So this means you could just pretend like your 1 and 2 don't exist because they don't mean anything, they have no consequence on your function. The function only cares about what it maps to, so it might as well be that B only has the element 3, and what do we find? How many functions can you make when you only want to map to this element? Well, it's going to be 1 to the power of 4, right? Because you only have one element in B really left, and you still have 4 elements in A you're mapping, so it's 1 to the power of 4. Okay, what if instead we decide to, let's say, keep 1, but not map 1 and 3? We want to map everything to 2, for example. Well, what is that going to look like? So we take a function, for example, where we don't map anything to 1 and 2. We're not mapping anything to 2 variables or 2 elements. Well, we might as well pretend like the 1 and 3 aren't there then. We're just mapping everything to 2. So what does that really mean? Well, how many possible functions can you create that only map to 2? Well, it's going to be 1 to the power of 4 again. So you find that when you want to map a function that doesn't go to 2 elements, it's going to be 1 to the power of 4 for each variation, each combination of this sort. So what do we find here? Well, it looks like it's just going to be 3 minus 2. Oh, yes, 3 minus 2 to the power of 4, which is just going to be 1 to the power of 4, right? It's going to be b minus 2 to the power of a. That's the kind of relationship I want you to notice. Now, you could, of course, do more examples if you're not convinced, but for the sake of time, and I think you're smart enough to see that this is the sort of pattern we're sort of recognizing at the moment. Okay, so far we have noticed that when you don't want to map one element in your function, let's say you choose 1, well, that's going to equal to b minus 1 to the power of a, right? That's going to be the solution of how many functions you can create that don't map to 1. If you want to know how many functions don't map to 2, it's also going to be b minus 1 to the power of a. And then when you want to find out how many functions don't map to 3, it's also going to be b minus 1 to the power of a. Well, what do we notice here? For this case, the number of combinations, the number of ways you can choose, if you remember earlier the word I chose, the number of ways you can choose whether you're going to not map something to 1, or you are not going to map something to 3, or you're not going to map something to 2, in this case is going to be 3 different ways. But we need to generalize it somehow, right? Because if we take, for example, our case with 2 elements, well, we're simply asking ourselves, well, how many different combinations can you not map to 2 elements? Well, that could be 1 and 2, or 1 and 3, or 2 and 3, or, you know, like, you get the idea. So what is that going to look like? Well, because we're using choose as our word in our logic here, you should think about our n choose k notation. So what does this mean? Well, the n, of course, means how many options do you have to choose from, and k means how many of them you're actually going to be choosing. So in this case, for this problem, we're going to be thinking, how many elements in B can we choose from, and how many of them are we choosing not to map something to? So what do we find? Well, for the first case, it's going to be, well, we have 3 here. Well, it should be something like 3, choose 1. We're taking 3 elements in our B, and we're choosing one of them to not map something to. What about the case where we're not going to be choosing 2? Well, that's going to be something like this, right? And what do we find in this case? Well, in this case, we find that we still have only 3 elements to choose from, but we're choosing not one element to not map something to. We're instead choosing 2 elements to not map something to. And what is this number going to be? Well, it's going to be 3 factorial over 2 factorial times 3 minus 2 all factorial. Now this is just 1 factorial, which is 1, so we're going to ignore that. So it's really 3 times 2 times 1 over 2 factorial, which is 2 times 1, which is going to equal 3, which makes sense. The only combination of 2 elements you can choose not to map something to is going to be 1 and 2, 1 and 3, and 2 and, oh, that's a very bad looking 2. 2 and 3, right? Those are the only combinations of the 3 numbers you can choose 2 of that you're not going to map something to. But nonetheless, this is going to be our notation here. 3, choose 2. Or, I'm so sorry, it's not going to be 3. The other thing I should note is it's not going to be 3. The 3 here is the size of our B, as I've said. So it's actually going to be equal to B, choose 1, B, choose 2. In this case, it was 3 because B is equal to 3. Our B up here is going to equal to 3 in this example. Okay, so we've got some more notation down so far. What else could we think of in this case? We've got a good bit of notation down so far, but we don't have enough yet to make a general statement for our underlined red, but we've got a big part of it so far. We know it's going to be the total minus some series of these sort of formulas. But there's something I should note. When we said earlier that let's just take one of these scenarios, right? One scenario where we choose one element to not count and we specifically choose the element 1. We're not going to look at all 1, 2, and 3. We're just going to look at the case where we're not going to map 1. So we're looking at this top line here and we're looking at one of the combinations that you can choose of elements not to map. So that's going to be something like this. So an example would be obviously we're not mapping anything to 1. So a function like this is something we would have included in our blue expression here. This is something we would have included over here. All of the functions that don't map to 1, this would have been one of them in this bracket here. Okay, well, something I should tell you is that in this blue bracket, it doesn't only count functions that look like this. It also counts functions that don't include 1, but also look like this. It also includes functions that might not map to one of the other elements, right? So when we're counting something like this, we're only setting a restriction on our 1. We're saying there's no way we are mapping something to 1. But we're not saying that you cannot map something to 3. We're saying you could just not map anything to 3. So it would include functions that look like this blue part here. Now you might be asking yourself, why is that a problem? Well, in this same line, let's look at the second combination that we want to include in our choose notation, right? What is the second type we're going to look at? Well, when you're going to not map 3, what is that going to include? Well, it's going to include the following. So what do we notice? Well, this function I'm circling in red is exactly the same as the function I'm circling here in blue. These are, by all means, identical. But what happened? We're, in this case, not mapping anything to 1, and we're not mapping anything to 3, and we end up counting just in this one line here. We're not even talking about the second line. In this one line, we're counting we've already found an example of where we're counting one function more than once, which is a problem. We only want to count this function once. We don't want to count it twice. So we're double counting things. We're counting them more than once because of this property that we're not setting limits on our second or our second and third and so on elements. We're only setting in this case, we're only fixing one element. So it would include cases like this. So how are we going to fix double counting a function just in our first scenario? Well, we're going to actually use our second case, our second scenario here. And what does that mean? Well, because for when we're counting or excluding, not mapping, better way of saying is when we're not mapping one element, because it would include functions where we're not mapping that one element and maybe another element, that means that we're double counting specifically functions that do not map two elements while doing the first one. So how are we going to solve this problem? Well, we're going to use the second one. What we're going to say is, well, because this is double counted, the second one here, this second line over here, includes the function that we've double counted, right? Everything here is going to go to the 2 in the middle. 1, 2, 3, A, B, C, D. This part here is included there. Now remember, we are subtracting what we don't want. So at the end of the day, this needs to be negative, which means this is actually -1, -1. This is going to be -2, but we only need to subtract this only -1. So we don't need to subtract it twice. So what are we going to do? We're going to add one of these, because this exists here and one of them exists here. So we're just going to add one of these down here, totaling to the fact that because we're subtracting this once, then when we choose a different one, we're going to subtract it again, subtracting twice. And then after this, when we get to our counting, when you don't want to map two elements in our second case, we're going to add instead. And when we add this, we're going to turn this -2 into, we're going to add 1 and get it into a -1, fixing our problem. So what we're going to do is we're going to do this negative plus sort of pattern. I've kind of fixed a little bit of the problem here, but I think you kind of noticed a pattern that if you had abnormally large sets, or just really massive sets A and B, this is really just going to equal to B choose n multiplied by B minus n to the power of A, where n is simply going to be the number of elements not mapped, right? In this case, n was 1. In this case, n was 2. So this is really the general idea we're going to go for. But we're going to notice that when we do something with 3, right, we're going to do minus then something with B choose 3 times B minus 3 to the power of A. We're going to be like, okay, well, now we're encountering the issue again of double counting, right? Because we fixed this here, but your sets can be much larger than just 1 and 2. They could have 3, 4, 5, 7, 18, 24, right? So you're going to notice we're going to have a negative here. You're going to double count again. So what are we going to do to fix that? Well, the next one over, we're going to just do addition. We're going to make it so when we're choosing 4 elements, the next consecutive logical choice here, choosing 4 elements to not map, we're going to make that positive. We're going to make it B choose 4 times B minus 4 to the power of A. And this is the pattern you're going to notice, is that for odd numbers of n, you're going to want to subtract. But to fix the double counting, you're going to want to add for even numbers of n. So what does this mean? This minus plus minus plus really just becomes, -1 to the power of, to the power of n. Right? When n is odd, it's just going to equal to -1. When n is even, it's going to equal to 1, which means we really can just turn this into a plus sign. We're going to add. So then when something is negative, we're going to subtract, and to fix the double counting, we're going to add again. This is the last sort of piece we really need to use to figure out this red part, is to fix the double counting, we're going to have to add this part in. So what is our total going to look like? Okay, we've done a whole bunch of math. What is the final formula that we found? Okay, well, we know that the total is going to be B to the power of A. And we want to subtract what we don't want. Well, what we don't want is all of these cases when we don't have 1 function mapped, 2 functions mapped, 3, 4, all the way up until B. Why are we going all the way up until B? Well, because if you have a function a, for example, the most amount of functions it can't map to is going to be everything in your codomain, right? You can't map to more than your codomain. That just doesn't make sense. So the most it cannot, in this case, right? We're not mapping one element, we're not mapping two. The most it cannot map is going to be all of them in the codomain. So that is why we go up until b. Why do we not go greater than b? Well, because let's say you add an additional element to b, right? Let's say b is greater than a. Your size of your codomain is greater than the size of your domain. Well, what you're going to find is you are always going to have functions that are not onto, because you will always have an element that won't have an element in the domain mapping to it, right? If b has more elements than a, you'll never get an onto function because you cannot say something like this. This no longer is a function. So that's why we don't worry about that case, because if b is greater than a, you're going to get that there are no onto functions. So that's why we only go up until b. So what do we get then? We then say that because we need to subtract all of these, it's kind of like a sum, right? You want to subtract this, and you want to subtract this, and you want to subtract this. So it's like a sum. It's all of these, right? So it's going to look something like this, right? We're going to have n equal to 1 because we're going to start with not mapping one element. We're going to go all the way up until b, as I just explained, and we're just going to plug our formula in, right? It's going to be negative 1 to the power of n times b choose n times b minus n to the power of a. This is really the formula to count how many onto functions there are between a set a and b from a to b. One more note I want to make. This is almost the final answer, although this is good enough if you want to use it. Notice you can actually put all of this into a sum. How can you do that? Well, notice what b is. B is really just saying, well, what if we don't map? Or sorry, what if we just not map anything, right? Well, b is like saying, what if we don't map nothing? What does that mean? Well, b is really just saying, well, what if you have negative 1 to the power of 0, b choose 0, times b minus 0 to the power of a? Well, negative 1 to the power of 0 is going to be 1, b choose 0 is going to be 1, and b minus 0 is going to be b, so it's just going to be b to the power of a, which is just going to be b to the power of a. Well, because we can write this in this form, we can actually adjust this a little bit and include it in our sum. So what do we get? We get the following. We need to reduce this to 0 because, of course, the total case would be as if you did not map 0 elements. So it's going to be negative 1 to the n. It's just going to be the same thing copied over here onto here. And there we go. This is our final answer. This is how many onto functions there are between two finite sets. For a function that maps from a to b is going to be this.